Let's look at a short section here, structures of metals and alloys. So this is looking at the kind of intricacies of metals. We won't do much chemistry with metals and metallurgy. That's a big form out in the real world, but we won't focus too much on it. We'll focus more on ionic and covalent bonding. But when we think of metals, their ions do not move. So this gives metals mostly a structure that's solid. However, what this is also you can see has overlapping orbitals of where those electrons are found. And this really causes what's called an electron sea, meaning that the water molecules and the electrons are free to float any which direction, which gives it the properties that it has. The fact that they're often opaque, can't see through them because they're tightly and dense. Good conductors of heat and electricity because these atoms would vibrate back and forth. And because they're in close contact, they're going to have this carry on of heat and electricity. Malleability, that the fact that you can bend it and being able to have very few interactions and still be able to be connected enables it to be malleable. And ductility just means you can put it into a wire, which means the fact that it can be drawn out and be still very thin, but still have strong attractions to, of course, support weight. Now, there's a thing about band theory. We won't really get into that depth throughout this year, but really you want to think of these working as a sea of electrons to where this enables us to have all of the structures, all the properties that we do see. So metals change based upon temp and pressure. So there's a lot of different shapes that lead to gaps that they can fit into, in which we can have different types of crystals. Now, you're not going to need to memorize these or anything. This is just here for demonstration purposes. So from this, you can see different metals have different available structures to them. Some are very complicated and different. Some got one, and that's all they get. It's like nickel, copper, zinc, all very much have the same ones. That means that you can make alloys with different metals, but you can't make them with all metals because some of them won't be able to have room to have the metals, or the different charges will not be able to really come together. So that's where we look at, you can't just mix all metals. There's only ones that really will work well. So alloys, there's two types that we'll look into. Substitutional, where some of the things are replaced. This can change the shape of the crystal, and it works only well when you have atoms that are being replaced that are pretty close in size. So you couldn't take a fluorine molecule and replace it with like a sodium molecule or sodium ion, fluorine ion and a sodium ion. You couldn't replace those. Well, I guess fluorine is not a metal ion, like tungsten, way down on the periodic table. So these are substitutional. So these are when you think of things that are, so much zinc and so much copper because they're really close to each other on the periodic table. Those are going to be more substitutional. Interstitial is a funny name for it. But what that means is that it actually fits in between the existing structure. So that means a very, very small ion will fit into a large ions that are around, and it'll fit into a very small hole. Don't worry about these numbers here. This is just the idea that they need to be much, much smaller. So this would be fitting something like lithium in a tungsten area, to where these are tungsten atoms and this is lithium, able to fit and slide right in. Again, provided that the attractive forces all line up. So what do you get when you actually mix these things? Well, if you look at this kind of little graph, you have pure chromium. I guess it melts at 1863, becomes a liquid. Pure vanadium melts at a higher temperature. Now, if you start mixing these together, so like a 90% vanadium with a 10% chromium, it gets lower and lower as its melting point. And you can see it's not 50-50. These things are acting very differently. Chromium and vanadium are very close to each other on the periodic table, so this must be a substitutional alloy. So when things get substituted down, you actually get to its lowest combined when you have 30% chromium and I guess 70% vanadium. Or that says mole percent vanadium, so I'm going to guess 30% vanadium, 70% chromium. You get to this lowest point of which it's going to be melting. Now over here, you have nickel and chromium, which nickel and chromium are a little bit different. They're pretty similar. And you get a whole variety of things. So when you have a whole bunch of chromium, or a whole bunch of nickel, it's going to be very different than when you start actually chromium added to it. So this will change the properties of the metals themselves. And sometimes you want to have a mix of both. And that's where alloys can be very useful. I should have read my previous slide. It said substitutional alloys. Interstitial alloys fill those holes, or at least many of the holes. So this one looks at carbon and nitrogen and hydrogen, making these kind of ionic compounds with the non-metal acting as a negative ion. So when you have all of them done, 1/2, a quarter, all of them, these result in very different types of properties. So titanium carbide, having all of those filled, very high melting point, much higher than titanium. However, hydrogen, who also has the fraction of holes occupied, much smaller ion, it makes it 450, where it actually decomposes, it breaks apart. So it actually decreases the ability for titanium atoms to hold on to each other. So when we think of this interstitial, it's kind of like this other area where you had, you have a jar, you got rocks. Is it full? You might say yes. Then you can add smaller rocks and is it full? Yes. Let's add some sand because we can still fill in more. Then you can add water. And so these are always just filling these atomic holes, which can be a difference in how you would have an alloy that could maybe increase the strength or maybe even decrease the strength based upon what you're looking for and the properties you're trying to match. All right, that's the end of this. Make sure you come in with any kind of questions. I'm here to help. Have a good one. Take care.